Okay, in biochemistry we'll take a small topic which is configuration in the case of sugars. When you take monosaccharides, only one monosaccharide lack asymmetric carbon, and that monosaccharide is dihydroxyacetone, is something like the glycine when you are considering in terms of the amino acid. So dihydroxyacetone is optically inactive, so that you can find out immediately when you have the structure. So an asymmetric carbon should have 4 groups surrounding carbon atoms. By rule, this should be the case, where A is not equal to B is not equal to D is not equal to E. Then this carbon we say asymmetric carbon, or chiral carbon. Chiral indicates in hand. So an asymmetric carbon has a tetrahedral arrangement where it is surrounded by 4 different groups or 4 different atoms. Now if you take here 2 atoms are hydrogen, this cannot be asymmetric. If you take this, double bond has come, it cannot be. Double bond, triple bond carbons can never be asymmetric. And this, if you take again, we have 2 hydrogen atoms, so it cannot be asymmetric. So that's why dihydroxyacetone is symmetric molecule. It is optically inactive. So there is no D-dihydroxyacetone, no L-dihydroxyacetone. The LD comes only when you have asymmetric center. If you take the simplest molecule in carbohydrates that have an asymmetric center, then it will be glyceraldehyde. So this is the carbon which is asymmetric in the case of glyceraldehyde. This cannot be asymmetric because there is a double bond. This cannot be asymmetric because there are 2 hydrogen atoms. So carbon 2 is asymmetric. Since it is asymmetric, it can exist in 2 forms. So this is the other form, which if you carefully see, it is a mirror image. So the only difference that we are seeing is with respect to the carbon 2 group arrangement, not groups. Groups are same, but group arrangement is different. Here OH group is in the 2-dimensional representation on the right side. Here the OH group is on the left side. Because they are mirror images, remember mirror images exhibit lateral inversion. You cannot superimpose one glyceraldehyde over the other. If I try to move this glyceraldehyde gradually and if I try to place here, hydrogen will superimpose with the hydroxyl group will superimpose with hydrogen. In other words, like our right and left hand, which we cannot superimpose, the Two glyceraldehydic forms are not superimposable. This one we call D-glyceraldehyde. Whereas this we call L-glyceraldehyde. Together, these two forms are called enantiomers or enantiomorphs. The simple definition for enantiomers is mirror images that cannot be superimposed. So naturally occurring glyceraldehyde is D-glyceraldehyde, and in that D, always remember, indicates configuration. It indicates configuration, it won't indicate optical activity. Now the difference between the two is, a configuration of a molecule we can identify just by looking at the molecule structure. So you draw the molecular structure on the board, on the paper, or anywhere. By looking at the molecule, you can decide whether it is D or L. But when you go for optical rotation activity, you have to do the experiment and you have to see whether the plane of polarized light is moving in the clockwise direction or it is moving in the anti-clockwise direction. That's why a compound may be D, but it may be actually levorotatory, and we have an example of D-fructose. D-fructose is levorotatory. It's called levulose. So that's important always to remember. Configurations can be identified by looking at the structure of the molecule, but optical rotations cannot be recognized by looking at the molecule. They have to be determined by experiment, and these are fixed values. Once you're given a set of condition, specific rotation value will be fixed. Most of the naturally occurring sugars have D configuration. So most common sugars are natural sugars, D configuration. And most D sugars have dextrorotation. One example already have shown, D-fructose shows levorotation. Even though we have most of the naturally occurring sugars in the form of the D configuration, there are certain sugars that will have L configuration. One example is L-rhamnose. One example is L-fucose. One example, L-idose, that is used in the formation of iduronic acid. So these are natural sugars in L configuration. So they are levo-rotated anyway because of that L configuration. Now when you take glyceraldehyde and when you describe the configuration, it's a relatively simple one because there is only one asymmetric carbon. When you go to the higher sugars, you get multiple asymmetric centers. When you have multiple asymmetric centers, how you can decide which carbon should be taken as the configuration carbon? That's the question. So which carbon is configuration carbon? Now the rule is relatively simple. The asymmetric center far away from the carbonyl group is taken as configuration carbon. This you can also write as penultimate carbon in the sugar. So if you take tetroses, configuration carbon will become 3 because there are 4 carbons. If you take pentoses, since there are 5 carbons, the penultimate carbon will be 4, so configuration carbon 4. If you take hexoses, since there are 6 carbons, the penultimate carbon will become 5, it will be the configuration carbon. Heptoses if you take, since there are 7 carbon atoms, 6th carbon will become the configuration carbon. So that's how you identify the configuration carbon in any given monosaccharide. The configuration carbon is that asymmetric center which is farthest from the carbonyl group, or it is a penultimate carbon. So depending on whether this penultimate carbon is present in the form of D-glyceraldehyde or L-glyceraldehyde, we decide whether the sugar is D form or L form. So take this example, a tetrose. So in tetrose, carbon 3 will be the configuration carbon. This carbon is similar to that of L-glyceraldehyde carbon. So this will become L-tetrose. Take another example. So you have 6 carbon atoms. This carbon atom will become, the penultimate carbon atom will become configuration carbon. It has OH group on the right side. So this will be D-hexose. Similarly, when you take a ketose, so we have 6 carbons again. 5th carbon will become configuration carbon, and that is on the right side. It will become D-hexulose, the ulose we use for ketoses. Ose, aldoses, ulose, ketoses. Now, when you have sugar molecules with more than one asymmetric center, like what we have seen in the case of tetrose, pentose, hexose, heptose, and so on, they exhibit diastereomerism. So, diastereomerism is a phenomenon where an asymmetric carbon contains multiple asymmetric sites and therefore exhibits more than 2 optical isomers. Those optical isomers we call diastereomers. The diastereomers are not enantiomers. So they are not mirror images. Basically, the idea of that is not mirror images. So take this case. So there is 1, 2, 3, 4 D-erythrose. This is D-threose. These two are diastereomers, but they are not mirror images. For example, if I have to write mirror image for D-erythrose to produce L-erythrose, then I have to rotate all the asymmetric carbons. This compound is L-erythrose. Now we can say these two are enantiomers, mirror images. Similarly, if I want for triose the L form, I have to again rotate all asymmetric centers 180 degrees. So this will become L-threose. Now if you see carefully, these are enantiomers. So you have to always remember diastereomers are not enantiomers, diastereomers are not mirror images. D and L forms, they are enantiomers, and D and L forms are mirror images that cannot be superimposed. The next one in this concept, diastereomer concept, is epimers. So epimers are diastereomers or isomers that differ in configuration around a single carbon atom. So epimers are isomers that differ in configuration around a single carbon atom. You have enzymes called epimerases that will convert one epimer into another epimer. The conversion of an epimer into another epimer is called as epimerization. So we can take the epimers with respect to the glucose. So this is the first molecule we have, D-glucose. This is the second molecule, the diastereomer. This is D-mannose. So now if you see both of them, carbon 1 same, carbon 2 they differ, carbon 3, carbon 4, carbon 5, carbon 6 all are same. So the difference is with respect to these two. So these two are C2 epimers. Similarly, we can take glucose and galactose. So this is D-glucose, this is D-galactose. When you look at the difference is seen at 4th carbon. So these are C4 epimers. So all epimers are diastereomers. Epimers are not enantiomers. Epimers are not mirror images. Mirror images will be given only for enantiomers. Whenever you change one enantiomeric form into another enantiomeric form, every asymmetric carbon has to be rotated so that the groups will be reversed on that particular carbon.